flat rigidity of a standard sphere. Okay.
Maybe I should. So we try to stand still over here. Am I in the picture or no? Can you? Okay. Yeah. Oh, yeah. Okay, excellent. Well, thank you so much. Very grateful to the organizers for putting on this show. For me, at least, and maybe for some of you as well, this is my first in-person conference since summer 2019, I think, something like that. It's also my first lecture in a year and a half when I'm not wearing pajama pants. So it's going to be a little bit different. I'm going to try to stand still. I usually pace a little bit when I lecture, but I guess the main thing is that you see the screen. Okay, so my talk is really mostly about CR geometry and the deformations of CR structures of the standard CR3 sphere. But the questions actually come directly from Kähler-Einstein metrics, and especially the log potential and its extension properties to the boundary. So first things first, I should report that this is a joint work with Sean Curry. I guess it's a total of maybe 3 papers that I will partially cover today, but the new results come from our latest paper. So let me start with the setup. So omega is going to be a strictly pseudoconvex, bounded strictly pseudoconvex domain in Cn. N has to be at least 2. Much of what I'm saying in the beginning can be, happens more generally in pseudoconvex domains, and they don't even have to be necessarily bounded. But for my questions to make sense, I want it to be bounded and strictly pseudoconvex. Oh, and I'm assuming that the boundary is smooth, C infinity. M is going to be my standard notation for the boundary. And what we want to do is, well, the first thing we want to do is we're going to consider the Kähler-Einstein metric in omega. And as I said, it doesn't have to be strictly pseudoconvex for that to exist. So there's a unique one with Ricci, or scalar curvature, I guess, if you want. Kähler-Einstein metric with scalar curvature -1 or -m+1 if you talk scalar curvature. And how do you find it? Well, Cheng and Yao showed, well, I guess it goes back to the work of Pfefferman. You study the complex Monge-Ampere operator, J. I'm going to have some other J's as well, but this J will disappear in the beginning. So J is this complex Monge-Ampere operator. It's the determinant of this matrix here. So the matrix is n by 1 plus n+1 by n+1. And we consider the Dirichlet problem, where we try to solve J of u equals 1, and u being 0 on the boundary. And if we can do that, then we get these Chen-Yao Kähler-Einstein metric with -1 Ricci by just taking log of u to a suitable power. And it's going to be a complete Kähler-Einstein metric in omega. And as I said, Cheng-Yao showed that there is a unique positive solution in the interior It's smooth in the interior, C infinity smooth. It's sort of smooth up to the boundary, but not C infinity. So this was realized already by Pfefferman. So the smoothness actually, technically, the smoothness that Cheng Yao proved up to the boundary is n plus 3/2 minus epsilon, but that was later improved by Lee and Melrose to n plus 2 minus epsilon. So Pfefferman started this in the early to mid 1970s, and he tried to solve this Dirichlet problem essentially by iterations in algorithm, where he tried to improve J. He tried to find a function, smooth function R, which was 0 on the boundary, so a defining function for the boundary. He wanted it to be smooth, and he would like it to be J of R equals 1. But his algorithm broke down at a certain step, and he realized, of course, why that was, and it turns out that there's a log term happening here. But his algorithm always gives us a smooth solution, C infinity. When I say smooth, I mean C infinity. Smooth solution to J of R equals 1 plus an error term that vanishes to the n plus first power on the boundary. And such a defining function is also unique modulo things that vanish to one higher order on the boundary, namely n plus 2. We call such a defining function Pfefferman defining function. And if you do the expansion here, you see what's going on at the power R to the power n plus 1. There is a coefficient there. And if you do a sort of a Taylor expansion in R, where R is a defining function, then you can take coefficients there that are smooth functions on the boundary. So the first coefficient here that I call O, which appears at R to the power n plus 1. So it's a smooth function, C infinity on the boundary. And that is sort of the obstruction to getting higher. Well, first, it's the obstruction to getting, when I present it this way, it's the obstruction for Pfefferman's algorithm to go through to a higher power. And then Lee and Melrose also explained this by showing that the Cheng-Yao solution U actually has an asymptotic expansion that looks like this. So we take rho and the any defining function. And then the asymptotic expansion looks like this. There are coefficients here, rho k, and then there's a rho to the power n plus 1, and then there's a log chapter. K and theta k's are smooth functions up to the back. So in particular, you can write this. There is a first term that looks like this, which is of course a smooth term. So this is a C infinity defining function. And then the next term is eta 1, rho to the power n plus 2. And here's your first log term. And it turns out that this function, eta 1, oh, it's n plus 2. So there's a rho to the power 2. And this is, so the first log term coefficient, when you restrict it to the boundary, is this function O that appears here, modulo some non-boundary shape, non-zero constant. There's some constant. So it's the obstruction function obstructs Pfefferman's algorithm, but it also obstructs the smoothness up to the boundary of the Cheng algorithm. Now, Graham Robin Graham actually showed, well, he showed a number of things. So here are the things that he showed that are relevant to this talk. First of all, he showed that O, which is the obstruction function, is actually a local CR invariant. Although the way I introduced it, of course, you have to have a global domain omega, and you need to be sitting, and that domain, the way I've presented it here, needs to be a domain in Cn. But Graham showed that you can actually define O as a local CR invariant, and the CR manifold doesn't have to be embedded. And basically what he did, he showed that the Dirichlet problem that I described can actually be made into a local Cauchy problem by prescribing one more piece of data on the boundary. And in that way, you get a local CR invariant. Also, he showed more interesting, well, not more interesting, but further interesting properties, namely, even though the obstruction function, if you look at the board there, obstructs the smoothness up to the boundary just to the next order in some sense, there is potentially another log term appearing at a higher order there. Graham showed that if the obstruction function is 0 on some open set, then in fact all the higher order coefficients eta k also vanish on that same set. So in fact, the only thing that remains in the asymptotic expansion of U is rho times eta 0, which are both smooth. And he showed more, it's not just an asymptotic expansion, but indeed the Chen-Yao solution extends C infinity to that piece of the boundary where the obstruction function vanishes. And another way of saying this is saying that there is a Pfefferman defining function, which actually satisfies the equation JR equals 1 completely. So, and by the Pfefferman defining function, you recall I require that to be C infinity up to the boundary. Okay. More terminology here. A strictly pseudoconvex CR manifold is then said to be obstruction flat if O is identically 0. And the reason you can talk about that in general is because of Graham's work, who showed it's a local CR invariance. Okay, well, let's talk a little bit about, I don't know what the title here is. I can't read the title of my slides. Zoom. So I forgot what the title is, but let's see what's on this slide. Well, let's first examine, as one always does, the unit ball in Cn, Bn. Then the Chen-Yao solution is easy to compute or to even to guess what it should be. And then you check that that actually solves the Dirichlet problem. Just take U to be 1 minus mod Z squared. And of course, this is smooth everywhere. And hence, by Graham's work, it follows that the obstruction function is identically 0. Or in our terminology, the unit sphere is obstruction flat. And again, since O is now, as I said, it's a local CR invariant, it follows that any CR manifold that is spherical, that is just locally CR diffeomorphic to a piece of the sphere, also is obstruction flat. Now the converse is not true. The obstruction function, while being a local CR invariant, locally it's not terribly strong as an invariant. So you can have strictly pseudo. Well, if I forget, all my CR manifolds are strictly pseudoconvex, and when I say CR manifold, I mean one of hypersurface type. And again, this follows from Graham's work. That it can certainly be obstruction flat on an open set U, even on a large open set U, without being spherical. And the way to show that is basically by solving Graham's Cauchy problem for the J operator with a suitable additional piece of data. So in fact, it turns out that you can approximate any strictly pseudoconvex CR manifold up to order 2n plus 4 by an obstruction flat manifold. Okay, so I claim that this leads to a natural question, as we all do. So this is the question that interests me. So locally being obstruction flat doesn't mean it's spherical, but the converse is true. However, is it true that if you take a global bounded strictly pseudoconvex domain, can it have obstruction flat boundary without having a spherical boundary? So we know of no such example. So that would mean that you have a bounded strictly pseudoconvex domain for which the Chen-Yao solution is C infinity up to the boundary. So we think the answer to this is no. Now, slightly more relevant to the new results I want to talk about today is question Q prime here, which is more general. I should point out, we still don't know the answer to Q, but being bold, we also pose a more general question, Q prime. Namely, what about more general compact strictly pseudoconvex CR manifolds that don't have to be boundaries of domains in CN? So here one notices a difference which is relevant to this talk between the lowest dimensional case, the lowest interesting dimensional case, namely three-dimensional CR manifolds, and higher dimensional CR manifolds. Because by Boutet de Monvel, if you have a strictly pseudoconvex compact CR manifold of dimension 5 or higher, you can embed it in CN, in some large CN, not necessarily as a boundary of a domain in CN, but certainly as a boundary or as a relatively compact, the boundary of a relatively compact domain in an algebraic variety sitting in a higher dimensional CN. Whereas for three-dimensional CR manifolds, it's known, I guess, initially by the work of Nierenberg and Rossi, that you can have such objects, three-dimensional, that are not even locally embeddable in any CN whatsoever. Examples are, well, the first known examples are these so-called Rossi spheres, where you put some exotic CR structure on a sphere. And I should also mention here, for those of you who are interested in the Bergman kernel, in 2D, or equivalently for three-dimensional compact strictly pseudoconvex hypersphere CR manifolds, it turns out that, so if you take a domain, go back to the original question, take a domain in C2, then the obstruction function coincides with the trace of the log term in Pfefferman's expansion of the Bergman kernel. Now, this is only true as far as we know in 2D. In higher dimension, there is some relation between the trace of the log term of the Bergman kernel and the obstruction function. As CR invariants, they're equal at the linear level, but we don't know if they're equal completely. But at least in 2D, it's known that they're exactly the same. And hence, this question here, Q, is related to the Ramadanov conjecture, which asks for what domains is it true that there is no log term at all, or the log term vanishes to infinite order at the boundary. So at least in 2 dimensions, we've been calling this the strong Ramadanov conjecture, namely that the answer to the question Q is no in C2. And that would be then saying that even if only the trace of the log term of the Bergman kernel vanishes, then it has to be spherical. Okay. And of course, I would say the general conjecture in higher dimensions to Q is that the answer is still no. But then I don't want to call it the strong Ramadanov conjecture because it's less obviously related to the classical Ramadanov conjecture. And I should say the Ramadanov conjecture itself is open in higher I should also maybe at this point take just a moment to go off in well, not in a tangent, but in a tangent compared to the main results of this talk. Namely, if you look at Q prime there, it asks for compact strictly to the convex CR manifolds more generally. And it turns out the answer there is yes, in higher dimensions. If the CR manifold is of dimension 5 or higher, there are compact objects, in fact, lots of them, that are obstruction flat, but not spherical. And the typical, so this is some, well, work in progress that I'm doing with Ming Xiao and Hang Zhu. Turns out if you take any, say, any compact Kähler manifold that admits a Kähler-Einstein metric, and then you take the canonical bundle over that, or the anti-canonical bundle, depending on the sign of the Ricci, and then you take the unit circle bundle in that. That is always obstruction flat. And in general, that's not spherical. In fact, it's known precisely, you can classify which ones are spherical, and they correspond to sort of Hermitian symmetric spaces. Okay. However, we think that for three-dimensional CR manifolds, the answer to Q prime is still no. So you cannot construct these things in 2D without having also the boundary being spherical. Okay. So here, I think what's the title here is something like what is known. And now I'm only going to focus on the lowest dimensional case, three-dimensional CR manifold. So this is one of the first results shown and I proved a couple of years ago in C2. So you take a bounded domain, you smooth strictly to the convex boundary, and you assume that M has an approximate infinitesimal symmetry. You can define that, of course, precisely. I don't want to go into that. But suffice it to say, suppose you have an actual infinitesimal symmetry, then it has an approximate infinitesimal symmetry. If you take something that has an infinitesimal symmetry and you deform it a little bit, it has an approximate infinitesimal symmetry. So for instance, if you take the standard unit sphere and you perturb or you deform the CR structure a little bit, then you still have an approximate infinitesimal symmetry. So you get, oh, I'm sorry. If it's obstruction flat, then M is spherical. Forgot the punchline. So the answer to Q here is no under this additional assumption. So if you go back now to the case of the unit sphere, then as I mentioned, if you deform the sphere a little bit inside C2, then you still have an approximate infinitesimal symmetry, and you get so-called rigidity. That means that if you deform something a little bit, then you don't have this property anymore. The only property, okay. So here's the result. Rigidity result, if you take a small deformation of the unit sphere inside C2, if it's obstruction flat, then it actually, the domain has to be biholomorphic to B2. In fact, it's slightly stronger, in fact, than saying that's the boundary sphere. Now, I wanted to emphasize here that in this case, the lowest dimensional case, most deformations, in fact, of the standard three-sphere are not embeddable. In fact, it's the space of embeddable deformations of the three-sphere forms a Fouché manifold in the space of all deformations. So it's a small thing. So the space of non-embeddable ones is in fact dense, and the complement of a submanifold. And I should say here, in higher dimensions, the analogous result to corollary 1, the second result here, is due to Hibachi that he announced back in 2 years ago around the same time. But it's only for n greater or equal 3, and it's really a perturbative. In fact, see, there's an asterisk there on small, I should say. We can actually describe how big the space, the set of deformations that can be allowed in corollary 1 is, because you can sort of describe how long the infinitesimal symmetry of the sphere remains an approximate symmetry of the deformation. Now, and again, I want to emphasize, in the case when, so I wrote here, n is greater or equal 3, then there's no difference between embeddable and non-embeddable deformations by Boutin-Monbel and some stability results. So if you perturb the unit sphere in higher dimensions, then in fact, all deformed structures are embeddable as boundaries of domains in Cn in the same Cn. Okay. So here's the main new results. So Sean and I, well, we thought we studied the space of embeddable deformations of the standard 3 sphere in another paper. And we went back to asking ourselves, well, what about the general deformations, those that are not necessarily embeddable? Do we still have this rigidity property of the 3 sphere? That is it still true that if you take a deformed structure, if it is obstruction flat, it's still spherical, even if the deformation is not embeddable? And at first we thought the answer is yes, maybe that's possible, and that would be interesting. So I'll come back to that. I'll answer that question. But before answering that question, I should maybe try to motivate a little bit why one would, well, first of all, if it's not embeddable, then of course the whole connection to the obstruction of the Chen-Yao solution goes away. So of course the problem still makes sense because, as I said, the obstruction function is a CR invariant, so it makes sense on an abstract non-embeddable structure as well. But what is the interest of it? Well, it turns out that you can still interpret the obstruction function as an obstruction function, but not to a Chen-Yao solution, but as sort of a real version of the Chen-Yao problem it's an obstruction function in conformal geometry. If you go to the so-called Pfefferman space, which is a 4-dimensional space, circle bundle over the compact map. It also turns out in terms of conformal geometry, the obstruction flat equation is actually the same as the so-called Bach flat equation in conformal gravity on the Pfefferman space. So there's still less connection to complex analysis, but there's still obstructions going on there. Okay, so before stating the main results, let's just review what we mean by deformations of the CR structure on the sphere. So we take the 3 sphere, the standard CR3 sphere, that is this 3 sphere with the CR structure it gets as the boundary of the unit ball in C2. Okay. So we usually denote it in this way, S3, H, J0. It's not really going to play a role in this talk. So just briefly, the H here refers to the contact distribution, the standard contact distribution, which is the rank 2 subbundle of the tangent bundle. And J0 is the corresponding CR structure or complex structure on H. That defines the CR structure, but you can also just think of it as the CR structure it gets by just taking a 1-0 vector field, even global 1-0 vector field in this case, and saying that spans the tangent, well, the 1, 0 tangent bump. Now we're going to keep the contact structure on the 3-sphere fixed and just deform the CR structure within this contact structure. It turns out that any contact structure, in fact, any CR structure is equivalent to one that corresponds to deforming it within the standard contact structure by a result of grade. I guess the CR structure needs to be isotopic to the standard one, but we're just going to look at small ones. Okay, and we're fixing a contact form as well. Again, just the standard contact form. Wrong button. There. And as I said, any CR structure is equivalent to one of this form. And you can describe it, the way we should think about it is you can describe it by a so-called deformation tensor. So that's this P1 here. The 1 and 1 refers to the fact that it's a tensor, but you can forget about that because we're going to fix the frame and the contact form. So you just think of it as a C infinity function on the sphere. And then you look at the 1, 0 vector field here, which is the deformed 1, 0 vector field. Has the phi right there. And of course, phi equals 0 is the standard structure. And then we're going to look at the equation, the obstruction flat equation, obstruction function O equals 0. And it turns out that that is a 6th order nonlinear PDE for this C infinity function phi. So we're going to try see if we can solve that. And to analyze this PDE, we're going to use Fourier analysis. So we're going to do decomposition into spherical harmonics, where it turns out, of course, as you can imagine, the equation O equals 0, since O is a CR invariant, it of course has a lot of symmetries, too many. So you want to pick sort of a look in a particular gauge where you get rid of some of these. I mean, if you take any deformed CR structure on the sphere, you start acting on it by contact diffeomorphisms, you get equivalent CR structure. Of course, the group of contact diffeomorphisms is huge, so that's too much. So we're going to look at a so-called slice theorem that also has the advantage that it identifies the embeddable structures from the non-embeddable structures. Okay, so the spherical harmonics, I'm sure most of you know what the spherical harmonics on the sphere are. Okay, now given a deformation tensor, we're going to consider its spherical harmonic decomposition. So I forget about the indices here that correspond to being a tensor. I just forget those. And I expand it in spherical harmonics. So phi sub pq are the spherical harmonic components of degree pq or by degree pq. And we introduce these two spaces, subspaces. And I have the slide of that. You can see, I'll just draw a picture. If you're anything like me, reading that doesn't help. So here's schematics. Here's P, here's Q. So this represents the equal lattice here. The spherical harmonics. Here you have Q equals 4. Here you have Q equals 1. And there are 2, including Q equals 1. This is D0 perp. The reason for the D0, well, the perp is that, in fact, it turns out that the orthogonal complement of this and of 2 is the tangent space of the embeddable, which we used to call D0, so we call this perp. And then other guy here is the prime for Epstein. The B stands for Burns Epstein, and I'll explain. It's this thing here. And the prime here on the diagonal, there's an additional condition. So you only get half of this. So now we proved the slice theorem in a paper where we studied the embeddability, and we introduced this slice because in this slice, well, first of all, this is a good slice. So it turns out that any CR structure sufficiently close is equivalent to one whose deformation tensor has its spherical harmonic decomposition supported in these two, the sum of these two spaces. You can get the zero. When you've done that, you've eliminated a lot of the action and contact. The only thing that remains here, or you can't really get rid of, are the CR homomorphisms of the standard. You can't really get rid of. But that's a five-dimensional proof you can have. So each feed that has the spherical harmonic decomposition supported in these two, the sum of these two regions, is not unique, doesn't uniquely represent the CR structure, but almost up to the homomorphisms. And now, yes, okay. So now, I guess that's what the next thing here is saying. Yeah. So that's the slice theorem part. Now the embeddability part here is you can exactly describe the embeddable ones. The submanifold of the embeddable ones are the ones that supported exactly here. That is all these components. Now, interestingly enough, so to sort of go a little bit farther here, I'm reaching the end of my time. When you look at the obstruction operation, remember we're trying to solve this equation. Now, as I said, this is a nonlinear six-order PDE. If you look at the linearized part of it, and the linearized part of it actually has a kernel. And it consists exactly of this region down here. The linearized operator is zero exactly in these guys, which is why we thought at first that we could actually find non-embeddable things that were obstruction flat, but not. So in particular, if you find something here that is not identical to zero, then it's not spherical, because it's unique up to the automorphism groups of the sphere, and the automorphism groups of the sphere fixes zero. So the only representative here that is spherical is zero. So we thought that since you can solve the linearized equation by perturbing it a little bit, doing some perturbative analysis, you can find solutions to nonlinear. But to go a little bit ahead of time, that turns out not to be true. You can do it modulo, you get some cool homology, but it's infinite dimensional. So I'm not going to talk about that. But so this is a picture. Now, some credits here. So the first slice theorem was proved by Cheng and Lee in the mid-80s. But they proved a different slice theorem. They had a different slice. So what we needed, we were trying to study the embeddability of the structures. And in their slice, you can't easily identify the embeddable structures from the non-embeddable. So we proved a different slice theorem where you actually can single out the embeddable ones or describe very easily the embeddable ones. Credits go to Burns and Epstein, who showed that anything that is in the Burns-Epstein region is in fact embeddable. And then there's work by Bland and Lempert along these lines as well. And then separate slide, that's to remind me that I'm showing a separate slide that I essentially drew on the board here. Okay, so here's the result. The result is that, in fact, the only thing that's obstruction flat is the standard CR in some form. So even though you can solve the linearized equation, you can't solve the nonlinear equation. So you have rigidity. The standard CR3 sphere is rigid under obstruction flat deformations is one short way of saying it. If you want to be more precise, you can say this. Okay, so what do you, as I mentioned by our slice theorem and embeddability theorem, the PDE theorem to prove is theorem 4. You just look in the slice and you prove that the only solution to O equals 0 is the 0 solution. Then you're done. And here, the topology that you need for the open neighborhood, you measure the topology in Fallenstein spaces. So you need 3 derivatives in L2 to be small, 3 Fallenstein derivatives in L2 to be small. Okay, so just a brief idea of the proof in 3 minutes. Okay, so what do? Well, first of all, you want to work with pseudo-Hermitian geometry. So pseudo-Hermitian geometry was introduced by Tanaka and Webster independently. And as I mentioned in the beginning, we fix the standard contact form. And once you fix the contact form on a CR structure, on the strictly pseudo-convex CR structure, you get a pseudo-Hermitian structure. So we have pseudo-Hermitian structures on all of these CR structures there. And as I said, the PDO for the obstruction function is a 6th order PDO, and you can break it up as a composition by first letting phi1 go to, well, when you choose phi1, you can get Q11, which has a name. It is Elie Carton's 6th order or umbilical tensor. And that is, in fact, a 4th order nonlinear partial differential. And going along with the pseudo-Hermitian structure are 2 other objects. Well, first of all, you get the pseudo-Hermitian connection. That's a nabla there. And the A11 is the pseudo-Hermitian torsion. And that's also a differential operator that you can write down. They're kind of complicated. And you really just want to deal with some qualitative properties of them. But then once you have these things, you can write down the differential equation for O, and it's sitting there. Of course, everything in there depends on phi itself also. So the covariant derivatives depend on phi, the Q11, the curvature tensor depends on phi, and the torsion depends on phi. Okay, so now the proof, for the proof, you have to carefully study the linearized operators that give you Q. So again, I've dropped the tensor indices on Q and the linearized operator for the obstruction function. And the qualitative thing you need about the nonlinearities are certain homogeneities. And I will mention that when we come to it. So you proceed by contradiction. You assume that you can find a sequence of deformation tensors tending to 0 that are obstruction flat. So you have these phi upper k with obstruction functions O upper k, and you can write it as epsilon k times something that you normalize in Fallenstein 3 space to have Fallenstein 3 norm 1, and then you have to get an epsilon k that goes to 0, and then you decompose normalize tensor into two parts. Take a projection on this part, which corresponds to the embeddable part, and then the sort of the back, non-embeddable, the thing that causes the non-embeddability. And that's really what we need to work with here. So the first thing you need to do I have 1 minute? Okay. If you think so, you're the boss. Okay. So the first thing you show is that nevertheless, the projection on the Bernstein region of the phi hat is actually on the order of epsilon k to the square. So it goes to 0. Now, this is the most tricky part, I would say, because the differential equation, even the nonlinear terms, we understand the linear terms pretty good, but the nonlinear terms involve up to 6 derivatives. We're only controlling 3 derivatives. So this is where you need to know a little bit about the homogeneity. Yeah, so you need some more qualitative information to actually prove this. So this takes up the most part of the proof. Now, once you know that, it's sort of clear what you want to do. So if you think of it's a C infinity function, obstruction function. You can also think of its decomposition into spherical harmonics. Of course, it's not going to be supported in this region, but in general, it's going to be supported in this region. And the idea is to show that the components, the 0, component of the spherical decomposition of the obstruction function is non-zero. Because then yeah, so we're trying to get into the contradictions. You want to show that it can. Okay, so how do you get the 0, component? Well, you just integrate the function around the sphere. Well, if you integrate the function around the sphere, since the obstruction function is supposed to be 0, you get 0. And then you do calculations with the differential equation. You integrate by parts. And then you identify the leading term in terms of epsilon. And it turns out that comes at epsilon squared. And this is the leading part of it. And then everything else is higher power than epsilon. You see here, everything here just concerns the non-embeddable portion kernel. Okay, so now to get the contradiction, you just need to show that this does not go to 0. So, well, it follows from that equation that this actually goes to 0, but we're trying to get a contradiction, so we're going to show it can't go to 0. And then basically you have to do some more integration by parts. In this, and again, you need to understand a little bit. So it turns out that the linearized Q operator, when you restrict it to this part here, as well as this part here, when you restrict it down here, behaves essentially like the sublaplacian. This behaves like the square of the sublaplacian, this behaves like the sublaplacian. But it's only true down here, not at all true up here. So then you get this lower bound, and then you are done because part 1 tells you that this one has to go to 1 because the other projection tends to 0. That's what we proved in part 1. And since it goes to 1, well, you contradict it too. So that's it. Thank you. Oh, thanks.
Are there some questions? Online? So, does somebody have questions online?
Yeah.
Does this theory, when this theory is formulated from less than C infinity, say cross CK, one-dimensional spherical boundary.
Yeah.
So you may have to modify it.
Right.
But would it make sense?
Yes. I'm trying to. So if you go back to so I mean, certainly if you drop the regularity of the boundary, you can ask similar questions. I mean, you can ask about the Cheng-Yao solution. I mean, you have a Cheng-Yao solution without any regularity at all, right? This is a result of Mach and Yao. Shows that on any bounded pseudoconvex domain, you can find the Kähler-Einstein metric, so you can solve the Teffermans-Dirichlet problem. And now you can ask how that behaves as you go up to the boundary. Now it turns out if you want to, you need some regularity because. For instance, if you allow Lipschitz, then it's not going to be true in general, because then you can, well, maybe in C2 it could be true, but in higher dimensions it's certainly not true because of the result that I mentioned with Ming Zhao and Hang Zhu. If you take a bounded symmetric domain, for instance, and you take, so on a bounded symmetric domain, you have a Kähler-Einstein metric, and then you take the disk bundle in the anti-canonical bundle, or the canonical bundle, then that is always going to be obstruction flat. But it's not, in general, it's not going to be spherical. But certainly you can add, but you have to maybe modify your conjectures. And I mean, in terms of just studying the differential equation, it's a sixth order differential equation, so you can study it with lower regularity CR manifolds. So yes, thank you.
Other questions?
Yes.
You mentioned that obstruction flat was a theorem invariant.
Yes.
It's far from having a classification of a manifold that could be obstruction flat without being the general case.
Yes.
Without being theoretical.
Yes.
What would be next invariant?
Yeah. So here's you give it in C2. So locally, here's, if you take any in C2 and you say something that's 0, if you take Chermoser local coordinates, then you can write the differential equation where you can write this way. And W is equal to squared plus sum A is equal to L is equal to 0 AKL, sorry, so these are called the Chernobyl coefficients. Now it turns out that you can always, if you fix, you can always find if you look at mapping W equals squared plus sum is the same as K, that's equal to let me write it. Sum K plus L that's equal to 8.
0.
Of higher order terms, you can always choose the higher order terms. You can fix these arbitrarily. Fix, and you can choose these so that this becomes obstruction. But you have a lot of and of course, if you don't choose these to be 0, it's opposite. You can oscillate anything up to order up to order 7. So you have lots of things that are not spherical. Because you know you can oscillate the sphere. By spherical thing, you can only oscillate up to order 5. But by an obstruction factor, you can oscillate up to order 7. And that's just a feature. In higher dimensions, you can oscillate to higher.
Other questions? So let's keep on